I have. Can y'all see that?
Yes, sir. Oh.
Yeah, well, I apologize. So bioavailability and bioequivalence, there are several methods. We talked about the actual calculation of bioavailability. So there are several methods. What I have methods used, methods of assessing bioavailability. So when a pharmaceutical company, when they submit a new drug application and they want to get a new drug approved, then usually bioavailability are required. And the Food and Drug Administration, they allow that particular company or those companies several different means to assess bioavailability, because this has to be written up in a report and submitted with the application. So usually there's going to be bioavailability data. And the four main things that can be looked at, we can use, the FDA will allow the use of, only one of these four is usually going to be required. They'll allow the use of plasma drug data. And I shared with you the equation for calculating bioavailability the other day. So with plasma data, if the company submits that type of data, then they're going to be submitting data that indicates the area under the curve. Area under the curve data, which you're familiar with that concept. They're going to be submitting information that pertains to the maximum concentration of drug. You know what Cmax is. We've talked about that with the absorption model. Okay. And then they're going to be submitting information also that pertains to Tmax, and I'll talk a little bit more about each one of these. We know that the area in the curve gives us a measurement of it reflects the extent of absorption. So the more drug that gets into the bloodstream, the greater the area under the curve is going to be. So remember, we said that bioavailability is a measurement that indicates the rate and the extent of absorption. So the area under the curve gives us an indication of the extent of absorption. The higher the area under the curve, the greater the extent of absorption. So that's an important parameter when we're looking at plasma drug concentration with respect to assessing bioavailability, the area under the curve. Okay. The area under the curve is usually when we're measuring it, concentration versus time. If we're looking at concentration versus time data, and let's say we have two formulations of the drug. Okay. We say we have A and B. Two different drug products now, not two different drugs. Remember, we're talking about dosage formulations or whatever. Then usually with the area under the curve, okay, the terminal portion of the curve, okay, for those two drug products, okay, is usually going to be the same value. So the KDL for those different drug products, okay, is usually assumed to be the same value. So if it's the same drug, the liver and the kidney, they're not going to handle it any different. They don't care whether the drug got there by an IV dose, intramuscular dose, an oral dose. So looking at the area under the curve assumes that the terminal half-life in the post-absorption phase, okay, for the drug product is the same. Okay. Now, the Ka value can be different. So the absorption rate constant, I mean, we expect that oftentimes we're gonna get a different Ka value for a solution of the drug versus a capsule that contains that same drug. Oftentimes that solution is gonna be absorbed more rapidly. It's gonna usually have a higher Ka value than, say, a tablet of that same drug will be. So we oftentimes can get differences in the Ka values. Okay. But generally speaking, the KEL values are gonna be the same. Okay. The take-home message here is that as we look at area under the curve, we have to be, kind of careful that we don't say too much give it. It's important, but it gives the extent. It doesn't tell us a whole lot about the rate. Okay, we can have a situation where two different drug products, concentration versus time. We could see something like this. A, drug product A, drug product B. Both of those could have the same area under the curve, but obviously drug product A is absorbed faster than drug product B. Okay. So even though these two drug products may have the same area under the curve, in other words, the extent of absorption could be similar for drug products A and B. It's obvious that the rate of absorption of A is faster than the rate of absorption for B. A is reaching its Tmax value at a shorter time than drug product B would be. Okay. So in a normal situation, these two drug products would not be considered as bioequivalent drug products. Because remember we said that I gave you those three or four definitions of it, but bioequivalent drug products, we said would be those pharmaceutical equivalents that are not significantly different with respect to rate and extent of absorption. So normally, under normal circumstances, now there was one caveat, we say if it's a sustained release or controlled release or an extended release preparation, and the designer, the manufacturer designed the drug product to have a slower rate of absorption, it's possible it could still be bioequivalent. But under all circumstances, for two drug products to be bioequivalent, they have to have the same extent of absorption. Okay. Under normal circumstances, these would not be considered bioequivalent, even if the extent of absorption is the same. Drug product A is being absorbed faster than drug product B, as indicated by the shorter Tmax value for drug product A. Questions? Drug product A has a faster rate of absorption, has a higher Ka value. We had real numbers here. Drug product A would have a higher Ka value than drug product B. They have the same KEL values. So remember that equation for Tmax. Okay, if the KEL values are the same, and I'm getting different Tmax values, then the difference must be in Ka.
Oh, right.
Does that make sense? Yeah. Okay. So that's not unusual when we are comparing drug products and we get differences in the Ka value. Normally, the KEL value is going to be pretty much the same. So that's what I'm trying to show you. So area under the curve is important. Another possibility is when we're looking at the maximum concentration. Of course, it's possible that I'm just showing you some possibilities. Okay? It's possible that I could have something like this. Again, let's call this A and B. A and B. And we'll say the area under the curve from 0 to infinity for drug product A is equal to the area under the curve from 0 to infinity for drug product B. Same thing here. We just assume. They don't have to be, okay, but we just assume to make our discussion. Area under the curve for drug product A, area under the curve from 0 to infinity is equal to the area under the curve for drug product B. That no signal thing is.
Do you mind turning that
You
off?
can
I
turn
think
it
that's the
off.
problem.
You hit the button.
Yeah.
Input, standby arms.
You gotta hit it again.
Hit it again. Thank you very much.
No problem.
Okay, so in this case, if the area under the curve for A and B are equal, okay. Again, it's obvious that drug product A is being absorbed faster than drug product product B, okay? But drug product A has a higher Cmax value. So when those companies are reporting on Cmax value, again, it would be so tempting to say that drug product A, okay, if we didn't look at the areas under the curve, it would be easy to say that, well, drug product A is more bioavailable than drug product B because drug product A reaches a higher concentration. So that's why the drug company said, no, we're not just gonna look at areas under the curve, let's look at Cmax too. Or we're not just gonna look at Cmax, let's look at areas under the curve also. Because if we just looked at Cmax here, with no regards to area under the curve, then it appears that drug product A, just looking at the Cmax value, is more bioavailable and it's having a higher Cmax value than drug product B. Okay? But when we also consider the area under the curve, then we can say, oh no, A and B are being absorbed to the same extent. They may not be bioavailable because A has a faster rate of absorption, okay? But the extent of absorption for A and B, if this is true, is the same. They're being absorbed to the same, assuming they're given at the same dose. Because of course, if drug product A or B was only given at half the dose of the other one, and I saw the areas under the curve was the same, then it would be like, well, one of them being absorbed to a greater extent than the other one. But assuming that the dose for A and B, for all of these, we're gonna assume we gave the same dose. Now remember the equation I showed you the other day, we can make adjustments for the dose. But to make the discussion simple this morning, I'm just assuming that the dose of A and B in all of these is the same. Okay. So, higher Ka value, same KEL value. I should have drawn those terminal lines parallel. Because the way I drew it right here, the post-absorption phase, KEL value is different here because those lines are not parallel. So I should have maybe drawn them parallel to each other. I'll see if I can make that correction. Let's go with that to cheat a little bit. So in most cases, the post-absorption phase, KEL values are going to be the same. Okay. Questions? Questions? No?
Right, Dr. Kelly.
Yes.
So Cmax, so how you said the area under the curve reflects the extent of absorption?
Yes. It's
Cmax,
not the extent, it reflects the extent.
it reflects the extent.
Yeah, so the more drug that's absorbed, the higher the area under the curve is going to be.
Okay, so for Cmax, it reflects the rate of absorption?
Well, we know that, you know that from your pharmacology and therapeutic studies, that concentrations generally are related to therapeutic or pharmacological effects. Okay, so that's one of the important reasons for measuring the Cmax value also. But if we just looked at the area under the curve, okay, if we just looked at the area under the curve here, in this case right here, if we were only looking at the area under the curve, okay, we could be misled because we don't know if the area under the curve is due to this situation happening, or another possibility is just looking at the area under the curve for A and B. Another possibility, there are several possibilities, but this could be a possibility, and we want to know. What if this happens? Just hypothetically. And you know all of those points ain't gonna be on top of each other. But let's just say that the x-axis is equal to drug product A, and the line is equal to drug product B. I mean, that could happen too. So now they have the same areas under the curve.
They're equivalent.
Yeah, they have the same areas under the curve again, okay? But now they have the same Cmax value, all right? So you see, this is a possibility, this is a possibility. So we don't sort out the difference between Cmax and areas under the curve. We don't know whether this is happening or this is happening. So now I'm a drug manufacturer and I need to come up with a dosing schedule for the drug or whatever the case may be. The dosing schedule, okay, is going to be different or perhaps different in this situation where the drug is reaching a higher Cmax value at a given time versus the dosing that I would give in this situation. Even though in both systems, I'm gonna say versus. In both of these, the extent of absorption is the same. if I assume that the area under the curve for A here, area under the curve for drug product A, again, is equal to area under the curve for drug product B. The extent of absorption is the same in both of them. But the rates are different. Here, drug product A is being absorbed faster. Here, drug product A is being absorbed at the same rate as drug product B. So these could very well lead to the dosing schedule being different. You know, maybe this might be 200, I'm just making up numbers, 200 milligrams every, 4 hours, every 6 hours. This might be 100 milligrams or whatever every 4 or 6 hours because of differences in the rate of absorption here versus here. Can everybody see that? I understand, if I've already told you that the areas under the curve reflect the extent of absorption, both of these have the same areas under the curve. I've specified that. So both of these situations have the same extent of absorption, but the rates are different. This is being absorbed faster.
So when you say rate, I keep thinking of like a rate constant, but.
A rate and a rate constant are not the same thing. A rate is a rate constant times some amount. I've preached that sermon a number of times. The rate is the product. If you look back at the equation that I gave you for the absorption model, I gave you rates and I gave you rate constants, A equals C times V, and you got KDL. I told you that the input rate was equal to F times D.
So that's just the rate.
F times D times KA. Okay. I'm sorry, that's not what I told you. It's similar to what I told you, but that ain't what I told you. I told you that the rate was equal to KA times F times D times E to the power negative KA times T minus KE, this is KEL, minus KEL, I'm not showing all that unit excretion and all that kind of stuff, minus KEL times A, okay? So again, this is a rate, this is a rate. KEL times A is the elimination rate, KEL is the rate constant. Ka times F times D times E to the power Ka times T is a rate, okay? This is an amount. What I just put that parenthesis around, that's an amount. Because the dose is an amount, F doesn't have any units. So that's an amount that's decreasing at the absorption site. Ka is a rate constant. So a rate is always some rate constant times the amount, okay? So in this case, okay, the rate of absorption for A and B is the same. The rate constant is the same also. In this case. In this case, okay, they have different rates and rate constants. Okay. The rate constant for drug product A, okay, is higher than the rate constant for drug product B. How do I know that? Because I know how to calculate T max, and if the KEL values are the same, the only thing that's going to cause T max to be shorter here, it must be a difference in Ka. Right? Any other questions? Okay, let me see here. Let me just review a concept that we talked about briefly when we were dealing with the absorption model, and it relates to area under the curve. Remember we said that in the absorption model that clearance was equal to F times D, or one way of calculating clearance was equal to F times D divided by the area under the curve from 0 to infinity. So with regards to area under the curve, and I think I showed this relationship, area under the curve can also count. Did I mess up? Somebody?
No, I was just repeating like F times D.
Yeah.
Oh,
Yeah, if it was an IV dose, we wouldn't have F there. That F is the absolute bioavailability. So area under the curve can be calculated as F times D divided by clearance total. Okay. So that's one way we can calculate the area under the curve. You know, in a bioavailability study, normally we give an IV dose, so we can get clearance from V times KL. The clearance after an oral dose and the clearance after an IV dose, just like KL value, is going to be the same. The volume and distribution are going to be the same. So if you're doing that assignment those graphs that I asked you to do for laboratory this week, you'll see that those 4 drug products, that the KEL value is pretty much the same for all 4. You'll see that the slopes are similar in the post-absorption phase. And there's an IV bolus dose there also. And you'll see that KEL value from the IV bolus dose matches up with the KEL value in the post-absorption phase from the oral solution, the oral tablet, and the oral capsule. That's if you're doing what I asked you to do. So as long as we have first order elimination, you know, doing in this model, then we can look at relationship. If we looked at, let's see who's here this morning. If we looked at a graph of area under the curve versus the dose, based on this equation. If we looked at area under the curve based on this equation, and I put area under the curve, that's from area under the curve from 0 to infinity versus the dose, what should that graph look like? Anybody? Describe it to me. What should a plot of area under the curve versus dose look like? I think we covered this one time in class. Huh? Somebody said a straight line. If I plotted the data, should it look like that?
Yes, sir.
Janae, should it look like that? I know. Autumn, should it look like that?
I don't think so.
I think it should be a little further.
What'd you say, JD? Why?
Well, if the dose is high.
John, what about it? You say you got something to say about it? What should it look like? That like that? Oh, where's my, what about this right here?
Can you repeat the question?
I'm asking, what should the graph look like?
The graph look like what?
In terms of plotting the data, I just had an example up there, and some people said it didn't look like that, so now I put another. Should it look like this?
Yes.
By show of hands. Should it look like that? Why not, I'm gonna draw some circles. Why not this? Why not that? Why not a graph that looks like the zeros are we just fill them in. Why not the filled circles versus X? Why would it look like that?
Because the initial concentration is 0. Is it because the initial concentration is 0? We don't have nothing in the body yet?
Okay, all I'm saying because the initial concentration is 0. But what I'm trying to get you to see is that, again, here we have an equation that describes a straight line such that, here's what I want to be. This equation is in the form of y, okay? And I put dose on the x-axis, okay? So dose is on the x-axis, okay? Plus b is equal to what in this equation? B in this is what?
It should be the initial.
No, B, what numerical value does B have based on this equation right?
0.
0. So going back to Kimi's explanation, I wanted somebody to explain it to me in terms of y is equal to mx plus b. But yeah, the initial concentration of y-intercept in this case is going to intersect at 0. In this case, is gonna have some positive value, which indicates that I have an area under the curve when the dose is equal to 0. How can I have an area under the curve if the dose is equal to 0? So this indicates a positive intercept. This would be wrong. You know, I can set this up on an examination or a quiz, and I'm trying to get you to understand that anytime you have an equation, okay, in the form of y units for p, I've told you that I'm gonna put area in the curve under the y-axis and dose on the x-axis. What's the slope of that line? In terms of the equation, what would the slope of that line be?
Positive.
No, I'm saying in terms of what the variables in the equation, in this equation. Describe the slope of that line in terms of what's in that equation. Anybody?
Should be positive.
What would the slope of the line be equal to in terms of those players in the equation? Now the players are A, U, C, F, D, and clearance total. Describe what the slope of the line would be in terms of those 4 things. What would the value of the slope of the line be in terms of A, U, C, F, D, and clearance? I'm not saying all 4 of those are going to be in the slope. I'm asking you to tell me, if I wanted to calculate the slope of that line, what would I use from that equation? What did you say, Press? Did you say anything?
I was thinking of what the X is, right?
Would be dose.
That's the y coordinate. I mean the x coordinate. That's dose.
That's dose.
I'm trying to get you to see the relationship y. Huh? Daniel, what's slope of that line in terms of the players in this equation right here? It's F over clearance, sports fan. I heard you, JD. I heard you. The slope of that line is F over clearance.
Okay.
Ain't nothing, but if this is X, then M is F over clearance. The slope of that line is F over clearance. That's a fair question. So I can calculate the slope of that line just like we've always done. Take 2 points on the line, calculate the slope of the line, set that equal to F over clearance. If I know clearance, I can calculate F, or if I know F, I can calculate the clearance of it. From a rearrangement of this relationship, right?
So when
Now,
you get
as long as the elimination is first order, okay, this line just stay straight. Now, if we get to the point where elimination is no longer first order, which we're going to talk about nonlinear pharmacokinetics before the semester's over. But for right now, you know, we assume that this is a linear relationship. But for drugs like phenytoin, as we continue to increase the dose, this line will start doing like this. It won't stay straight. As long as the dose is low, and the concentration is low, then we'll have first order kinetics. So right now, we don't need to worry about this curve portion. I just want you to recognize that if we're in this region here, all that stuff we just said, all bets off now. The slope of this line, and when we get up in this region, is not necessarily F over clearance anymore. Okay? Because things have become non-linear once we get to a real big dose. But as long as we have this type of relationship, where there's linearity between the area under the curve and the dose, then we can draw some conclusions. So the slope of this line in the first order region, the linear region, is equal to F over clearance. Question, I saw somebody had a hand up.
So
Yes.
if we derive with the answer, how do we know what goes to F and what goes to clearance? Or just one answer?
You got to know 2 of those to calculate the third one. Slope you can get by calculating the slope of the line, which you want to do.
And if we get
so
the
you need
answer,
to know F in order to calculate clearance, or you need to know clearance in order to calculate F. If you got an equation with 3 things in it, you got to know 2 of them in order to calculate the third.
I'm saying when you take it from the point of the line.
Take what from the point of the
You
line?
said take 2 points to get the answer.
No, I said to get the slope of the line, you take 2 points, just like you've always done.
Yeah, so you said slope equals F over KO,
But you just calculate the slope of the line. You got an area in the curve
So
here,
would,
you got an
so
area in
would
the
that
curve
one
here.
number
So,
equals
so
out to that?
sports fans, AUC1 minus AUC2, 1, 2, over dose 1, we'll just call this dose 1, we'll call this dose 2. Dose 1 minus dose 2 is equal to the slope of that line. It's equal to the slope of that line. It's equal to the slope of this line. You take 2 areas under the curve and 2 doses. You don't got to guess because it's the same sermon I've been preaching for the whole semester. Just let the equation guide you. The slope is equal to the difference between 2 y values, areas under the curve, over 2 of the x values. What's in the x position? Dose. So the slope of that line is equal to area, one area in the curve minus the second one over 1 dose minus the second one. That's the slope of the line. Any equation in the form of y equals mx plus b, okay, you ought to be able to calculate slopes and intercepts just based on the equation. Okay. So going back to what you learned a long time ago, you know, if y is equal to 3x, we covered this the first week of class, but if y is equal to 3x plus 4, you know, that line, like you learned a long time ago, it's going to have an intercept of 4, and it's going to have a slope of 3. Slope is equal to 3. Well, you know that by just looking at the equation. But if you generate some fake data, x equals 1, y, you know, like you learn how to do in 4, 5, 6, whenever, you can take any 2 points on this line, okay, and any 2 y values, okay, and calculate the slope. It's going to always come out to that 3 right there. Guaranteed. If you want to take a point here and a point here, it's still going to come out to 3. It's going to still hit it. Intercept with 4. Okay. Is that okay? That's all. That's okay.
I'll ask you after class.
Okay, so plasma data is important. And here goes. Then we can also look at urine data to evaluate area under the curve. Now, plasma data is the ideal way, okay? Because ultimately, you know, we want the drug to get in the bloodstream. But sometimes, like we've talked about before, we might not have a convenient way to look at drug concentrations in the plasma. We know that oftentimes drugs are concentrated in the urine. Sometimes that makes the drug easier to measure in the urine. So we can do some things with urinary excretion data too. If we're the drug company and we're submitting this information to the Food and Drug Administration in our new drug application. We're submitting our bioavailability data. We can also have the option of looking at urinary excretion data. Urinary excretion. Now we don't do 1 and 2 necessarily. We can, but you know, the Food and Drug Administration is going to require at least one of these 4 things accompany that new drug application. Okay? That NDA as it's called. And remember I told you that the absolute bioavailability, if we're looking at urinary excretion, we said that we could look at the AU infinity for the test dose. I think we call that A, the test product, over the dose of drug product A, divided by the AU infinity. Now, don't get AU infinity and area under the curve mixed up. The area under the curve had to do with plasma data. This AU infinity is the cumulative amount of drug excreted in the urine. Okay? So AU infinity for the reference standard divided by the dose of the reference standard. Okay. So we haven't spent a whole lot of time talking about urinary excretion, at least doing the kinetics associated with it. I was looking at the lecture schedule before I came to class this morning, and I kind of skipped over urinary excretion for oral dosing. So if we have time after we finish this, we might come back and talk a little bit more about the kinetics associated with urinary excretion, okay? But if we give an oral dose or a dose that requires absorption, okay, according to the absorption model, okay? Then if we look at the total amount of drug excreted in the urine versus time, this is after we give a dose, okay? That plasma concentration time curve is gonna go up and it's gonna plateau off at some point in time. And that final amount, we talked about this before when we talked about the IV dose. That final cumulative amount over here on the y-axis is AU infinity. AU infinity. Okay. So the faster the drug reaches AU infinity, the faster the rate of absorption. If you think about it for a moment. The faster the drug reaches its final, AU infinity is the final total amount of unmetabolized drug, if you recall when we talked about IV dose. It's the final cumulative amount of unmetabolized parent drug that reaches the urine, that's excreted in the urine. So the faster I can get to AU infinity, in other words, you know, let's draw a separate example.
Say that one more time about the curve.
I'm gonna say it one more time, but I don't like that line there. I'm gonna say it, but as I say it, hopefully I can show it, and it'll make more sense. Let's try it this way. Let's try it this way. So let's call this drug product A. We'll call this one A. We'll call this one B. We assume that the AU infinity value for drug product A, we're going to assume that it's the same AU infinity value as drug product B. Which one of those drug products reaches its AU infinity value faster? Remember, we're not talking about two different drugs, we're talking about drug products, okay? Same drug in both of them. Which one reaches AU infinity faster? Okay, so we will conclude that drug product A is being absorbed faster. Remember, bioavailability is a measurement of the rate and extent of absorption. So in terms of rate of absorption, assuming I gave the same dose for A and B, I'm gonna keep the same dose to make things simple, but we don't have to have the same dose for A and B. I can adjust for that. But assuming it's the same dose, then from a data set, a graph that looks like this, we will conclude that drug product A is being absorbed faster because it's reaching its AU infinity value faster. Think about it for a moment. It can't get into the urine unless it hits the bloodstream first. So it had to be absorbed in order to be excreted in the urine. So here, the extent of absorption is the same. Remember, the extent has to do with how much. So the extent of absorption for drug product A and B is the same, but drug product A is being absorbed at a faster rate than drug product B. So that can tell us something about the relative, I don't want to say relative, but the comparative bioavailability of drug product A and B. We can conclude right here. Now, a lot of times in bioavailability and a bioequivalent study, we have more than just two products, okay? But I'm just showing two so you can understand the concept. So drug product A, based on urinary excretion data, is being absorbed faster at a faster rate because it's maxing out faster. But in this case, the extent of absorption is the same for those two products. Are they bioequivalent? Under the normal definition of bioequivalence, would those two drug products be bioequivalent? A and B? Huh? I heard somebody say no, but then you hear it from them. Are they bioequivalent based on the definition of bioequivalent drug products? Thank you, Janae. Okay, under normal circumstances, these would not be considered as bioequivalent because they have similar extent of absorption, but the rates are different. Under normal circumstances, now again, we had that one caveat. We said that the rates could be different if that's by design and it doesn't have a significant clinical adverse effect. So under some circumstances, these could be considered as bioequivalent. But that would have to be a design feature that the manufacturer put in there, like if it's a sustained, if it's controlled release preparation, we would expect the drug product A is gonna be absorbed more slowly, if it's an extended release preparation. But under normal circumstances, the usual definition of bioequivalence, okay, these would not be bioequivalent drug products, because even though they have similar extent of absorption, the rates are different. As evidenced by the fact that drug product A is being reaching its AU infinity value faster than drug product B. Is that understood?
What makes it similar extent of absorption when you say that?
Because they have the same AU infinity value. The extent just represents the amount of drug that's excreted. So they have, you know, here we're just gonna assume that AU infinity for drug product A is equal to AU infinity. So that's the same extent of absorption. Extent represents how much. The rate represents how fast. So for two things to be bioequivalent, they had to have pretty much the same extent and rate of absorption. But we said that we can make an exception for the rate if that difference is by design, and if that difference in the rate does not have any clinical or therapeutic consequence. Okay. So we have a lot of extended release products on the market that are absorbed more slowly, but it doesn't adversely affect clinical or the therapeutic outcome. So they can still be considered as bioequivalent to a conventional drug product. Is that clear?
The only question I have, if you were saying the faster that AU gets to AU infinity, I didn't see the end, like I didn't understand that part. Were you talking about the rate?
I'm saying at some point in time, remember when we were IV bolus dose, we said that AU is just a cumulative amount. So the cumulative amount of drug in the urine at 5 hours is going to be more than the cumulative amount at 1 hour. Eventually, I'm going to reach a point where no more drug is coming out in the urine. Eventually, I'm going to reach the final amount of drug in the urine. That's AU infinity. That's the total of that's unmetabolized drug too, by the way, the parent drug. We're not looking at metabolites. Just to refresh your memory, I don't want you to leave here saying, well, Dr. Felder told us that metabolites are not in the urine. The metabolites can be in the urine, but that's not what this AU value is for. It's the unmetabolized drug. That's what we're looking at. Okay. So the more of that unmetabolized drug that gets into the urine, the greater the extent of absorption. The more of that the faster that unmetabolized drug gets into the urine, the greater the rate of absorption. So drug product A has a faster rate of absorption than drug product B. They have the same extent of absorption in this example here. Does that answer your question, Janelle?
Yeah.
Any other questions? Okay, I'm gonna stop right there, and then we'll continue with have a little bit more on our urinary excretion data, and then there are two other that the use of plasma data and urinary excretion data. These are the two most common ways that we assess bioavailability. Plasma data and urinary excretion data. Of those two, if I had to decide which one is more commonly used, it would be plasma data. Which one is more reliable? I would say plasma data also, with urinary excretion being a close second. Now, we're going to talk about a third and a fourth method, that's discussed in your textbook also. And they're not used quite as often, and they're not as reliable as the use of plasma data and urinary excretion data. But if you can get plasma data, that's the ideal. If you can analyze or assess bioavailability using plasma data, that's really the way to go. But urinary excretion data it's a close second. Okay? It's almost just as reliable. Not quite, but it's close. Questions? Yes, ma'am.
So for the absolute bioavailability, you know how you have that equation right there? So what if it says like relative bioavailability? It would be the same equation, right?
No, relative bioavailability is a different equation. maybe I,
It's from the
with
text.
relative bioavailability, you know, both of these, okay, plasma data or urinary excretion data, okay, to get absolute bioavailability, I have to give, maybe I didn't write that right. That's a good point today. I think I didn't write that right. With absolute bioavailability, I didn't write this right. So change this in your notes.
Isn't that the one where stock is,
We need to give an IV dose for absolute bioavailability. Because the way I had it just now, that's really for relative bioavailability. That would really the equation for relative bioavailability. For absolute bioavailability, I need to give an IV dose if there's one available. Okay. Of drug, you know, whatever this drug is. Yeah. So Janae, thanks for pointing that out to me. But yeah, because they're not the same. Relative bioavailability and absolute. So yeah, anytime we do an absolute bioavailability, in the denominator is an IV dose for absolute bioavailability. Yeah.
So
That's a
this
good
whole
observation.
time you were preaching about relative bioavailability?
Say that again?
So this whole time it was about relative bioavailability?
No, everything I told you is true. I just wrote the wrong equation.
Oh,
I just wrote the wrong equation. I wrote the equation for relative bioavailability. This is absolute bioavailability. It should be an IV dose. The way it was before was assuming that I was using the full dose of the test product and the reference data.
okay.
That's relative bioavailability.
Okay. That's okay.
All right, I'll see you guys tomorrow.